Hello and welcome to another presentation, this time on logarithms and geometric sequences. We're going to do this in two parts, firstly logarithms and then secondly geometric sequences, mainly because logs can occasionally be used in a geometric sequence problem but not vice versa. So let's just give you a quick reminder about what logarithms are all about. Okay, log base 2 of 8 is 3, that is factually correct. Now you might wonder why. Well, it's true because 2 cubed equals 8. In other words, and this is often what I say to students, logs find powers. We have no function in maths without logarithms that locates a power, that finds a power. And funnily enough, that's exactly the principal use of a logarithm. So yeah, log base 2 of 8 is 3 because the little number to the power of the number on the right hand side equals the bigger number. Let's give a couple more examples. Log base 10 of 1 is 0. Why is that? Well, it's because 10 to the power of 0 is 1. Log base 4 of 8 is 1.5. That's true, and it's a little less clear, because 4 to the power of 3 over 2 is 8. And that's because if you had 4 to the power of 3 over 2, you'd square root the 4, then cube it, landing you to 8. Okay, let's try a couple where we need to find an unknown. What would log base 3 of 81 be then? Well, we need to, sometimes it's easier to rewrite it as in index form, and it becomes a lot clearer to see what the answer is. We just do the little number to the power of the right hand side is the bigger number, and we get 3 to the x is 81, and therefore x is 4, because 3 to the power of 4 is 81. Let's try one more of those. Log base 2 of x is a half. Now this time the unknown is in a different position. It's always easier though, I think, if you rewrite it in the form of index form. So 2 to the power of 0.5 is x, and then we can just see what x is, because 2 to the power of a half is the square root of 2. So that's how logarithms work. That's the general way we use logarithms. But the next big topic in logarithms is something called log laws, how we manipulate logarithms. Well, there's a series of 3 or 4 laws I like to teach my students. Here's the first one. It's the one really we've just met. Log base a of b equals x, if and only if a to the power of x equals b. That essentially tells you how to undo a logarithm. There's some other laws as well though. There's the addition law. Log base a of x plus log base a of y is log base a of x times y. This is essentially exactly the same as the index law, which says x to the power of a times x to the power of b is x to the power of a plus b. You add the powers when you're timesing. Well, with logs, when you're adding the logs, you multiply those values which are within the logarithm. So you get log base a of xy. Funnily enough, with subtraction, it works pretty much exactly how you would expect. It means that you're going to divide them this time when you're subtracting them. So log base a of x minus log base a of y is log base a of x divided by y. Finally, there's the power rule. Log base a of x to the n equals n log base a of x. And you're gonna see these rules in action very, very soon. I'm sure it's just reminding you about some of them anyway. Now, those rules all only work provided the base is the same. I'm not going to show you the rule for mixed bases, how you change the base of a logarithm, mainly because it doesn't really come up in A level, and it's very rarely of any use, I find. Anyway, there's always other ways around you can do it. But yeah, so those are the 4 rules, I'm gonna show you for the moment. Okay, let's give some example questions of what we might need to use logarithms for. Let's say we had a question which said solve 5 to the power of x is 7. Well, as I just explained originally, logs find powers. So if you ever have a power which is unknown, and it's not obvious, like 5 to the x equals 25, you might find it useful to use logs. Now, all I'm going to do to solve this is I'm going to take logs of both sides. Now, I'll be honest with you, I wouldn't normally write down the base 10. If the base 10 isn't written down, you just presume it's base 10. Actually, the working would work in any base. It doesn't matter what base you're dealing with for the logarithm, but we'll write base 10 there just for clarity. All we've done is taken log base 10 of both sides there, by the way. What I'm going to do next is I'm going to use that rule where you can flick the power down in front of the logarithm. So the x flicks down in front of the logarithm. And then we have x times log base 10 of 5 equals log base 10 of 7. Finally, I can just divide the logarithm over, because this is simply a number an ugly number like that, no doubt, but it's a number that your calculator knows, we can now just do log base 10 of 7 divided by log base 10 of 5 equals 1.21 to 2 decimal places. And sure enough, if you do 5 to the power of 1.21, you should get an answer very, very, very close to 7. So that's a good example of what logs are really used for. Let's try a different kind of question. Let's solve something like this. Log base 5 of 3x plus 95 equals 2 plus log base 5 of x plus 3. Now in these kind of questions, my suggestion to students is always the same. Marry up the logarithms, by which I mean put them together using log laws. So the first thing I'm going to do is put the log base 5 of x plus 3 on the left hand side. The next thing I'm going to do is I'm going to use another log law. Log a minus log b is simply log a over b. So I can write this instead as log base 5 of 3x plus 95 over x plus 3 equals 2. Now here's the bit where students often get stuck actually, because they forget how to undo a logarithm. Remember, the way we undo a logarithm is we do the little number to the power of the right hand side equals that which lies, the big term, within the logarithm. And so we're going to get 5 squared, which is 25, equals 3x plus 95 over x plus 3. Once you've done that, really everything else works just as if you were solving a normal linear equation, and you should, if you work that around, there's a few more steps which I've omitted, but you should get x is 10/11ths. Okay, so that's an example of a logarithm question where you're actually solving a function with some logarithms involved. Let's try something a little bit different though. Let's try something like this. Now this is an example of what I describe to students as a quadratic in disguise. That's because if you were to let 5 to the power of x equal u, you would actually have here u squared minus 4u plus 3 is 0. Because if u is 5 to the x, u squared would be 5 to the 2x because of the way power laws work. So we can actually factorise something like this to give us 5 to the x minus 3 in one bracket and 5 to the x minus 1 in another. If you multiply those brackets out, you'll see, yep, absolutely, it multiplies out to give the line above. Once we've done that, we proceed as normal really. We end up with 5 to the x equals 3 or 5 to the x equals 1. Now we can use logarithms on the left hand side in the same way as we did before. You'll end up with log 3 over log 5. Forget writing the little base 10 because your calculator, if you just press log on your calculator, it's working in base 10. You should end up with that result after a little bit of manipulation with log laws, and you get x is 0.7. For this one on the right hand side, you can pretty much do it in your head. You can see 5 to the power of 0 is 1. So that original equation had two solutions, 0.70 to 2 decimal places, and x is 0. Okay, let's move on to geometric sequences. Geometric sequences, I'm sure you'll remember, they are sequences in which any sequence of numbers has a common ratio. In other words, you multiply by the same number each time to get from one term to the next, or divide, because that's the same as multiplying by the fraction. More simply put, it's just any numbers then where you multiply by a constant value to get from one term to the next. So here's a few examples. Powers of 2, 2, 4, 8, 16, 32, 64. You're doubling each time. You're multiplying by 2 each time. Next one down, we're multiplying by 3 each time. The next one down, we're multiplying by a half each time, so we can be dividing by a term. And that gives us this general result. We have a first term a, just like in arithmetic sequences we call the first term a. But rather than using d for common difference, we use r for common ratio, so r will stand for the common ratio. So any geometric sequence can be described as a, then the next term as ar, and so for example, if we take this last sequence here, a would be 10, r would be a half, so we've got 10, 10 times a half, which gives me 5, 10 times a half squared, which gives me 2.5, 10 times a half cubed, which gives me 1.25, so on and so forth. Now the nth term for that, I hope you can just kind of see that the nth term is going to be ar to the n minus 1. Because, you know, the first term is ar to the 0, if you like. The second term is ar to the 1. The third term is ar to the 2. So the nth term is going to be ar to the n minus 1. We'll come back to that formula in a second. Okay, let's talk about finding the sum of a geometric series. Let's say you start with the sum. The sum of n terms is going to be a plus ar squared, so on and so forth, till you get to the nth term, which is ar to the n minus 1. What I'm going to do here is prove the sum formula for a geometric sequence. We could multiply this all by r, giving us r times the sum equals, now each term should be times by r, so we end up with ar squared, ar cubed, all the way up to ar to the n. Now we do the sneaky trick, and the sneaky trick is to subtract. So if we do Sn minus Rsn, this one minus this one, on the left hand side I'm going to have Sn minus Rsn, but on the right hand side I'm going to have A, okay, but then AR minus AR will cancel, AR squared minus AR squared will cancel, AR cubed minus AR cubed will cancel, AR to the n minus 1 will cancel with AR to the n minus 1 here, and then you'll have a minus AR to the n on the end. And so it will simplify really nicely. All we need to do next is factorise. So, sorry, I haven't done anything there. So let's factorise the results out. I'm just factorising out the Sn on the left hand side and the 1 minus r and the a on the right hand side, and now just divide across, giving us our formula for the sum of n terms in a geometric series. Remember, a sequence is just a sequence of numbers. A series is where you're summing that sequence. So this is the formula for the series, the geometric series, the sum of a geometric series. Okay, so let's have a look then finally at the sum to infinity of a geometric series. This only works if the common ratio is trapped between 1 and minus 1. Otherwise, the sum to infinity is infinity itself. The sequence diverges, as they say. But provided that the common ratio is between 1 and minus 1, there will be a finite value to the sum to infinity. And this is quite simple. It's simply sum to infinity is a over 1 minus r. It really comes just straight from the sum formula. If you consider r to the power of infinity basically tends towards 0, if r is between minus 1 and 1, you end up with that equation there. Okay, so let's have a look at the useful formulae we need for the next few questions, because we're going to go straight into the example questions here. The useful formulae are an is ar to the n minus 1. That's the formula for nth term. We've got Sn is a times 1 minus r to the n over 1 minus r. That's the formula for the sum of n terms. And finally, we've got the sum to infinity, which is just a over 1 minus r. Okay, we're going to be using all those formulae in the next 3 questions. Let's have a look at them now. Let's say you were asked to use some sigma notation. You were asked to evaluate that. Now, always with sigma, I often, if people don't know what to do, I say, have you tried writing out the first 3 terms of the series? Because that often just lets you know what you're dealing with. If we write out the first 3 terms of this one, or the first 3 terms and the last term, for the very first term, you're going to get 3 times 2 to the power of 1, which is 6, plus the second term is going to be 3 times 2 squared, which is 12, plus so on and so forth, right the way up to the 6th term, which is 3 times 2 to the power of 6, which is 192. Well, I hope you can see that this is simply a geometric series, and we just need therefore the sum formula. So Sn equals a times 1 minus r to the n over 1 minus r. A is going to be 6 here. R is going to be 2, because we are timesing by 2 each time to get to the next term. And the number of terms is going to be 6, because they want us to add the first 6 terms. Plug those values in, and you end up with... Oh, sorry. I've gone backwards. I'm ever so sorry about that. Let's just get back to where we were. Plug that into the formula, and I believe that comes to 384, I believe. 63 times 6, that looks right to me. 378, sorry. 378, I apologise. So yeah, that will come to 378. If we try this one looks a bit different. We're actually summing to infinity this time. I can see that because we've got an infinity sign on top of the sigma. Think of the first 3 terms once again. We just have minus 1.5 plus 0.75, because when you do an even power you're going to get a positive value, minus 0.375, so on and so forth. And that's going on to infinity. So we need the sum to infinity formula. Now the first term here is minus 1.5. The common ratio is minus a half. Notice the common ratio is negative. That's why the signs are alternating. So we're going to have a as minus 1.5, r as minus a half, and if you simplify that, you get the answer minus 1. So if you were to do minus 1.5 plus 3/4 minus 0.375, so on and so forth, infinitely long, your answer will eventually, well, it won't eventually get to it, it will converge upon the value of minus 1. Okay, let's do some questions without sigma in them. Let's consider this question. The third term of a geometric sequence is 162, and the sixth term is 6. Find the first term and the common ratio. Now, this isn't talking about the sum of a geometric sequence. We're just looking at nth terms here, so we need that formula. an is ar to the n minus 1. Now, because we've got the third term is going to be ar squared, and that equals 162. Remember, you're dealing with ar to the n minus 1 in this formula. Likewise, for the sixth term, you're going to get ar to the power of 5, and that equals 6. And this is the position we're in. Now, this is very similar to the way you approach arithmetic sequence questions of a similar type. But at this point, what I would suggest you do is divide those two equations. If we call this one equation 2, and this first one equation 1, if you do 2 divided by 1, you're going to end up eliminating a, because a divided by a is 1, r to the power of 5 divided by r squared is r cubed, and 6 over 162 simplifies to 1 over 27. We can then cube root and get r is a third, plug it back in, and you find a is 1458. Hopefully you're happy with that. Cool. Okay, the very last question we'll look at then. A geometric series has first term 2 and common ratio 3. What is the smallest number of terms needed for the sum to exceed 1 million? And this shows very powerfully how big geometric sequences become. And they do become very large very, very, very quickly. Okay, we're going to be using this formula because we're dealing with the sum of a sequence this time. And we can see our first term is 2, so a is going to be 2. Our common ratio is 3, so r is 3. N is actually what we're looking for here, the number of terms needed for the sum to exceed 1 million. So I'm actually going to write 2 times 1 minus 3 to the power of n over 1 minus 3. I want that to be larger than 1 million. So we'll start simplifying this. Firstly, 1 minus 3 is minus 2, and 2 divided by minus 2 gives me minus 1. So that minus 1 can just sit outside the brackets. What I'll probably do next is apply the negative throughout the brackets, which will just switch the signs around, so that now you've got 3 to the n minus 1 is bigger than 1 million. I would probably, and I'm going to work on the left-hand side of the screen now, add 1 to both sides. Sorry, I'm going to do it in the next bit. Apologies for that. So 3 to the n is larger than 1,000,001. And this gives me, now is a crucial time, because it's just like the 5 to the x equals 7 that we did earlier. We're just looking for a power. What I'm going to do is take logs of both sides. And that's exactly what I've done. I've taken logs of both sides. Now I'm going to use that log law, which allows me to flick the power down. And now finally, I'm going to divide by log 3. So I get n is larger than log of 1,000,001 over log 3. You can work that on a calculator, and you get n is greater than 12.5, and so the smallest value n could be is 13. And sure enough, you can check that at the end by plugging n is 12 and n is 13 into the formula. You can see that 12 isn't quite large enough for the sum. I think you end up with about 500,000, but at n is 13, you're much larger than that. You're much larger than 1 million, and so you're in a solid position. We've solved our problem. Okay, I hope all that makes sense. Best of luck in the unit assignments this week, and yes, good luck with the rest of the course. Bye bye.